The name of this video is a loop E from V. That is, we intend to first find the electrostatic potential V, and from V to find the electrostatic field E. For what problem? A problem we already encountered in a previous video, which is that of a charged loop. So in 3D, the loop again, this is the loop, and I want to find, if this is my loop, the electrostatic field on its axis, so normal to the loop surface, to the surface which contains the loop. So in 3D, let's sketch it as follows. This is my loop of charge, which is characterized by a linear charge distribution with constant density lambda equal the total charge Q over the loop divided by 2 pi capital R, where capital R is the radius of this loop. As always, let us choose a cylindrical coordinate system where this is the z-axis. And this is the r-axis. Accordingly, this one is the bar phi axis. This is the origin of such a coordinate system. We intend to find the electrostatic field due to this charge density. So first we begin by isolating here an infinitesimal element of length dl. This arc dl is equal to capital R times d bar phi, where this angle is the angle d bar phi. This point here is capital Q, is an infinitesimal source point. We want to observe the field due to this and eventually the entire circle, which we call gamma. At any point on the axis, let's say this point capital P up here. Of course, if you choose a point outside the axis, it's a very complicated problem. This distance, QP, between the observation point and the charge point, we call it R, Q, P, and is given by the square root of capital R square plus Z square under square root. Great. So we also know that this infinitesimal element is characterized by a charge dq, which is equal to lambda dl, and therefore lambda capital R d bar phi. All right, so now that we know all that, we can simply use the integral form, since this is a continuous charge distribution, for the electrostatic potential in 1D for a linear distribution. Therefore, the electrostatic potential V at point capital P, our observation point, this we can write it as 1 over 4 pi epsilon naught the integral on line gamma of dq divided by rqp. This distance here. Great, with respect to this coordinate system, therefore we can write this as 1 over 4 pi epsilon naught, the integral between 0 and 2 pi in d bar phi of lambda r, the radius, capital R, divided by rqp. Okay, this is a simple integral where clearly we already see that this is rqp. Rqp depends only on z, so this potential will be only a function of the variable z, which is our degree of freedom. We already know this from a previous video when we use Coulomb's law in the superposition principle, for example, to find the solution to this problem. So in this case, this integration is rather simple. This just gives me a factor of 2 pi. These are all constants of integration. So the result down here is going to be, after a simple calculation, lambda times capital R divided by 2 epsilon naught square root of r squared plus z squared, which is r qt. So 2 epsilon naught, therefore cancels with the 2 here, square root of capital R squared plus z squared under square root, not to forget. Okay, so this is our electrostatic potential, which again is just a function of z. Okay, great. So with this, we can finally use all this knowledge in order to find from V, which was very simple, simpler even if you want, than what we've done with Coulomb's law and the superposition principle. Now, eventually, we want to find E from this knowledge of V, which is given by minus the gradient of V. But V is only a function of Z, so the gradient in this case, it should be partial derivative of this is only, since it's only one direction, it's going to be minus the total derivative with respect to Z of V of Z. It has to be a vector along the only available direction, which is uz. Therefore, if we perform the calculation here, we obtain minus lambda r from this minus here, divided by 2 epsilon naught. This exponent gives me minus 1/2, because it's square root in the denominator. The whole quantity times the derivative with respect to z, which is 2 times z, 1/2 minus 1 minus 3/2. So divided by capital R squared plus z squared to the power of 3/2. And this goes in the uz direction. We can further simplify this result, obtaining in the denominator 2 times epsilon naught, exactly what we have here, capital R squared plus z squared to the power of 3/2. And in the numerator, we have lambda r, capital R z, in the uz direction, to the power of 3/2, which is exactly what we found previously. So at 0, for example, we get a 0, which is the same result as we found by means of Coulomb's law and the superposition principle. Of course, if you want, you can also represent this object as a function of the total charge q, which is given by lambda times 2 pi capital R. So you can express it either as a function of lambda or as a function of q, if you choose to do so. So this is our result. The electrostatic field is given by this quantity here along the z axis, as expected. So again, the point of this problem was to begin to find the very simple scalar function, the electrostatic potential V, for a loop of charge. From that, to use the definition of V, which is such that E is minus the gradient of V, and therefore finding a vector field from the scalar field, which is very easy. That's it.